Hello everybody, my name is Sevan. In this video, we are going to look at an example about wave interference. So this one is a case where a car travels between two radio transmitters, and we're going to see how the transmitted waves from each transmitter is interfering, and then what is the signal observed by the car. And then we're going to write a MATLAB code, and we're going to plot the signal strength received by the car as a function of the car's position. So let's look at the problem. If we look at a mobile communication or a radio system, so examples are cell phones or a amplitude modulated radio transmission, AM radio, it's not easy to cover a whole area. So you have a city, you have a district, you put a transmitter, and then you're transmitting and trying to cover a whole area. What happens is usually your signal gets attenuated and you need to add more transmitter. But when you add more transmitter, it will not always improve the signal strength and the coverage. Now we're going to look at a simplified example here, and we will see how the radio waves interfere destructively at some locations. If you remember your physics classes, you have waves. If you sum two waves, like two sinusoidal waves, for example, depending on their phase, they may interfere destructively. For example, you're doing something like a subtraction operation and the waves cancel each other. Or they can interfere constructively as well, which means you're actually summing two sine waves and you increase the amplitude, the strength of the signal. So this is just a simplified case we are going to look here. There are other types of issues causing signal degradation, such as multipath fading as well. From only one transmitter, you can also observe this effect of destructive interference, because the signal is, for example, in an urban environment, reflected from large buildings, and then it can interfere destructively as well at a given position. So this is a simple example. We are looking at a scenario as shown in the figure, where a vehicle, a car, is traveling on the roadway and it receives signal from two sources. Now what we're going to do is we're going to plot the signal received from the car for the car locations between -50 and +50 meters for this case. The units are not written much in meters, and the car only travels in road, so the y, the altitude or the y direction, y coordinate of the car is not changing. It's just changing in x direction. And the locations of the transmitter and receiver is given on the left, as you can see, and the transmit frequency is 100 megahertz. It's something like an AM radio transmit. So the first thing we're going to do is I'm going to start a pen, and then we're going to start writing an equation. I mean, it's nothing actually complicated. I'm going to go back and do it here. What we are going to do is we are going to calculate the distances between the transmitter and the car. For example, the first one is here. It's called the TX1 path. It's the distance between transmitter 1 and the car. So how we write this one? Let's call this distance D1. And then as we can see, if the car is at 0, 0 location, it's so easy to see. But when the car is traveling, when the car is moving, so what happens is we're actually creating a triangle. And then this triangle, quite nice and easy to solve, because it has a 90 degree between two sides of the triangle. And if you remember Pythagoras theorem, what we're going to do is we are basically calculate the hypotenuse. So you can see now D1 is this for this case. And we can call this side of the triangle A and this side of the triangle B. And as you remember, the distance of D1 will be A squared plus B squared in a square root. But A is actually changing according to the car's position. So if you look at A, what's A? A is the distance, the y distance between the car and the transmitter. So the car is always at y equals 0. So this is easy to find actually. We can just say this is dy1. Why? Because it's given in the question. Squared. See, now let's look at the B. Here B is the distance in terms of x. So we're trying to calculate this one. And what's happening here is Actually, now we are using the x coordinate of the transmitter, which is the dx1, and then we're gonna do minus the car's location. So we will call it xv. So this is car's location. Let's call this xv squared. So as you can see now, if I put them together in the same, so let's do it in another slide. It's going to be much easier to write. Let's call this d1 equals, we're going to do a big square root, and then it was dy1 squared plus dx1 minus xv squared. Okay, that's quite nice, but we need to use this distance information as a part of the wave propagated from the transmitter. So which means the wave propagation through a distance is going to give a phase delay or a time delay. So from this distance we need to find the time. How long does it take in terms of time the signal to go from transmitter to the car? So that's the most important information for us actually. So what I'm going to do is I'm going to define a T1, and then T1 will be, any guess? Yes, it's the distance divided by the speed of the travel. So if you remember again from your physics classes, this is an electromagnetic wave, the radio transmission. So it travels at the speed of light. So the travel speed is around 3 times 10 to the 8 meters per second. So this is the travel time. So if you can calculate the distance in meters, then we can find the time delay. That's quite easy. And then if you look at the d2, you know, we have another equation to solve actually. d2. That's the path, the second path from the transmitter to the car, tx2. So again, this is very simple to the first one, because the car is not moving in y direction. What we're gonna do is we're gonna say dy2 now, because the y component of the car's location is always 0, plus what I'm gonna do is dy2 minus exactly the same equation, but written for the second transmitter now. And then if you wanted to calculate the time delay, we are going to use exactly the same equation shown here. So our equations are quite clear now. What we can do is we can go to MATLAB and start writing it. Yeah, just write 2 equations so we can solve this question. So I'm just switching to MATLAB. So we will start a new script here. I'm going to click this button. We're going to say new script, and let's save this one first. We'll say save as. Let's call this test. I can't call it test because I already have a file called test. Okay, let's call this car example. Yes. Now it's an M file created here. Now I'm gonna write quickly what we described. First, I'm gonna define the parameters given in the question. For example, it's not given, but we know the speed of light is 3 times 10 to the 8. So in MATLAB we can write it quite easily in this format. So this means exactly the same as 3 times 10 to the 8. So this is exactly the same thing. And we are defining everything in meters per second. So I'm not writing it here, but it's quite easy to remember. So then the second information given to us is the transmission frequency, which is 100 megahertz. So again, this is exactly the same as before. It's 100 megahertz, or 100 times 10 to the 6. And now we're gonna look at the locations of the transmit and receive. Transmitter 1 and transmitter 2. So the location is given as 0 and 20 meters. So I'm going to define dx1 as 0. We're coming back again, as you can see. It's written as dx1 here. We are looking here, dx1, 0. And then now I'm going to write dy1 as 20 meters. So I'm putting these semicolons at the end so MATLAB doesn't give me an echo. So I'm going to do the same thing for the location of the tx2. It's 50 and 40. Let's do that one as well. Now I'm going to say dx2 it's the location of the second transmitter, which is 50. And then what I will do is I will do dy2, which was given as 40. Now that's quite good. And then to start with, you know, xv, the car location, as we said, is changing from minus 50 to 50. But first of all, we're just gonna try to calculate it at a 0 location. So let's assume car is at 0 position, and then we will just write the transmission equation, or the sine waves or the cosine waves, and we will try to see what's happening at location 0. So one thing I need to create to plot the cosine wave, you know, I want to check the signal transmitted from the transmitter, is to write a cosine wave, because it's transmitting cosine wave. And inside the cosine wave, what we're going to have is a time unit. You know, inside the cosine wave, we have something like 2 pi ft, which is the frequency and the time. So I need to define a time first. Let's define the time. Let's define an fs for the sampling frequency, and we're going to use it as our units. So on the Nyquist says it should be at least 2 times the transmit frequency, or the highest frequency possible, but we are not going to be limited to the Nyquist. We're just going to say let's use 100 times. So we have a good resolution. And now I will calculate the TS, which is 1 over Fs, sampling period. And then I'm going to define a time signal. T starts from 0, and then it's getting incremented by TS. And then now we're going to say when it finishes. So what I want roughly is, let's have 3 cycles of the signal we're transmitting. So I'm going to say 3 divided by Fs. F0. So this will give me a 3 cycle sine wave or cosine wave. And then I'm going to write a cosine and sine function, but inside these functions we need to integrate the time delays. So what I'm going to do is I'm going to start doing some calculations. So let's say calculate the delays here. So let's go back and look at our drawing. So what I'm going to do is I will just write down this equation exactly here. This should be straightforward. I'm going to say d1 equals square root of, inside this, let's say dy1 squared plus dx1 minus xv squared. So this is the same equation we written, and then the time delay is calculated by dividing the distance into c, or dividing the distance by the speed. And then d2 is exactly the same thing, so I'm just copy pasting and then I'm just updating the parameters here. So everything becomes 2 here. We're calculating d2, and we're using dy and dy2 and dx2 locations for the transmitted 2, and now this will give us time delay to t2. So now what we did is we written the equations, and now what we're going to do is we're going to say received signal. Let's call it R. So received signal will be a cosine. Let's call it a cosine wave, a summation of 2 cosines. So I'm going to write down the first cosine wave. So the first signal transmitted from the transmitter 1. So this is the signal transmitted from the first transmitter, but this is not the received signal from the transmitter. Sorry, received signal by the car. The received signal by the car is this, because the signal is delayed by t1. It takes that much time for the waves to travel. And for the second signal, the signal coming from the transmitter 2, I'm going to do exactly the same thing. And then I forgot multiplication. Let's do it. We're going to say t minus t2 this time. So this is the received signal. Let's plot it and have a look. How does it look? Does it look like something we expect or not? What I'm going to do is I'm going to say figure and then plot t comma rv. And then what we can do it actually, yeah, this is quite useful. This is quite good, but maybe we can have a reference as well. So let's have a reference signal, so it will make sense. The reference signal will be the signal transmitted from receiver 1 or receiver 2. And also, I didn't mention before, but in this case, what we are assuming is both transmitter and receiver are synchronous. So they both start at the same time with the same phase. So the signal is exactly the same. So what I'm going to do is I'm just going to transmit a signal. Or try to write the same thing again, but this time I will not have any phase delays. And let's fix the error in the code. So this is the S, the signal transmitted from. So I'm going to plot that one first, and I'm going to do a hold operation, hold the figure, and then I'm going to plot the received signal. Sorry, T comma R. Is it correct? Yes. So this one is wrong as well. T comma R. So it all looks T comma S. Sorry, transmitted signal, and then this is the received signal. Should we run this code? Let's have a look how what's gonna give us. So when I run the code, it's gonna execute every line by line, and then we made a small mistakes here. Let's correct that one and then run again. And then this time it runs. So let's look at the figure. So we received the figure and it shows 2 cosine waves. It's quite nice. And the blue one is the first one, the transmitted signal, and the red one is the received signal. We can observe immediately 2 things. If I can put a data point here, for example, I will quickly show you. So the magnitude of the received signal is actually larger than the transmit signal. If you look at the transmit signal, the maximum is 1. If we look at the maximum point, maximum amplitude of the received signal, it's more than 1. In this case, when the car was exactly at 0 position, the waves interfered somehow constructively, so they didn't cancel each other. And obviously there is a phase shift as well on the receiver side. So signal is shifted and the amplitude is slightly large. Okay, that's good. Now what we're gonna do is we're gonna actually change the D1, D2, or effectively T1 and T2 as a function of XV. So how it's gonna work? Let's have a look. So in this case, actually we can do a small trick. So instead of writing lots of cosine functions, we can use exponentials. So what I'm going to do is I'm going to write R signal again here, redefine it as an exponential. So if you remember Euler's formula, so we can write cosine or sine waves as exponentials. And in this case, I'm going to actually write it as 2 different exponentials. Now I will show you quickly what I'm going to do. It's 2 times pi times f0 times t. So this is the first part of the signal. As you can see, it was t minus t1. What I'm going to do is I will say this one multiplied with exponential. So I'm just separating the phase. It's exactly the same as writing it in size, but later on this might help us to do the calculation slightly but in a better way. And then t1. But one thing I forgot, this is actually a minus t1, so we should write minus t1. So it's exactly the same. And then we have the other cosine coming from the receiver too. So it's not a minus actually, it's a plus. We are summing them. And then it's exactly the same. Oh, sorry. One thing I forgot is this should be e to the j omega t. So we're gonna put the imaginary number here, I. So it shows that we are actually rotating around the unit circle between real and imaginary domains. So this is our signal, and this one is f2. So some of you probably noticed that this is not exactly the same with this equation, because it's not a cosine actually. This is summation of a cosine and sine if I just write it like this. But what I can do is I can look at the real part of this signal. The real part of this signal is exactly the same. So the real part of this exponential is a cosine wave. Exactly. So if you don't remember, we can do some of the examples to refresh your memories, but in this case we're going to assume that we already know that. So I'm going to plot the same figure again. So now what I'm going to do is copy paste from here, and then now I can't plot R like this, but what I can do is I can plot the real part of the R. So when I plot this side of the this side of, if I execute that part of the code, what I get is exactly the same. So I'm going to put them next to each other so you can see. So this is exactly the same figure. So we realized, or we written a code that does exactly the same thing using exponentials. Now, the nice thing is, now we can define an XV here. Now I'm going to create a new cell here in MATLAB. Sorry. Now we're going to define an XV, and XV will be changing now between, sorry, it's an equal sign here actually, between -50 to 50. And then in MATLAB, this means I'm just creating numbers from -50 to 50, and increment is by 1. I'm just going to try to increase the resolution a bit, so I'm going to increment by 0.1. And then now what I need to do is I need to redefine this. Why I need to do that? Because, you know, if you remember when you were doing matrix operations or vector operations versus operations with scalars or just numbers, the difference is there is only one type of multiplication between two constants, but if you're doing matrix operations, what we see is two different type of multiplication: a dot multiplication, a dot product, or a cross product, cross multiplication. So for this case, everything is a dot product. Actually, we want to multiply them one by one. So because XV become a vector or an array of numbers, now I need to put those dots there. So which means, you know, I'm doing an operation on an array, and then I want to do the multiplication, or in this case the square operation, one by one on every element. So now D becomes something like this. So we are slightly improving the formula. And now what I'm going to do is, from this signal, now I'm going to show you a small trick. From this one, what we want to do is, we actually don't need to look at the whole signal, because it's a cosine wave modulated by this, you know, changing according to this frequency. What I can do is I can change the shape slightly by doing this. For example, let's put them in brackets, and then we can slightly simplify it. Let's get rid of this one as well. And if I have these two, another thing I can do is, I know this is going to be constant, and then I just need to observe the phase differences, because at every given point, what I'm going to do is I'm just going to get the maximum of this signal effectively. You know, I want to calculate a certain part of the signal. That's the strength. If I was looking back on this figure, so from this figure, I don't need the whole cosine signal changing according to t. What I needed, I just need this point. This is 1.056. I just want to find the maximum strength of the signal. So to do this, what I can do is I can actually get rid of this part of the signal. So I'm going to quickly show you something. If I had this signal, and if I was plotting the real part of this signal, and I will call this let's call this the strength of the signal R strength. What I can do is I can look at the maximum point in this signal. Let's run it again. See. Evaluate selection. Okay. Do you see? Now this is exactly the same as the measurement I was making. 0.5. It looks like 0.56, but probably here I do not have the resolution to show the whole number, but this is the number. And now let's look at this trick. I'm going to show you that it's actually just a function of the phase. So we don't need to consider. So I did the same operation again. Now this time it showed a minus, so because I was looking at the other part. But what we can do is we can just do an absolute value operation. So we don't want to find the negative or the positive thing. We just want to find the absolute value of the signal strength. And if I run this one again, let's say evaluate selection, what I get is, yeah, exactly the same. So this is the phase of the signal. That gives us if the interference between the two waves are destructive or interference, or how they are changing according to the phase. Now what I'm going to do here is I'm going to do a new plot. What I'm going to do, I'm going to say figure. Now let's plot. Now I'm not going to plot things according to time, because time is not important. Now the thing important for us is the car's location. So I'm going to plot R strength, signal strength, according to the location of the car. So let's try to run this and see if it's working. Okay, I don't want the maximum value actually. Sorry, I need to remove that one. I'm just double checking. Yes, I just want the string as an absolute value, and now I can show you signal strength according to the car's location. And if I wanted to put some let's say labels on the figure, I would do this as well. I will just quickly type it and replot it, and now you can easily see what's happening. So when the car moves between, let's say, minus 50 to 50 meters, this is the vehicle position in meters, what's happening is the signal is first constructively interfering with each other, and there are these points where signal totally cancels out. And this happens quite a lot, and this is a function of the frequency, actually. So if you change the frequency of the signal, these ups and downs, the location of the down points and up points will change as well. So I think that's the end of this example. I'm just going to quickly go back and remind you what we did. So we looked at an example, a car traveling on a road, receiving signals from a transmitter, and there is two transmitters, and we calculate the received signal from the car, and then we find the strength of the signal, the maximum signal received by the car, and then we plotted it as a function of the vehicle's position. Thank you very much for listening. Bye.